All right, these are your 10.3 notes, which are about ellipses. An ellipse is very, very similar to a circle. Remember, we defined a circle as the set of all points equidistant from one fixed point called the center. An ellipse is the set of all points so that the sum of the distances from two fixed points is a constant number. An ellipse is the set of all points so that the sum of the distances from two fixed points is constant. In this picture of the ellipse, these two thumbtacks are like the two fixed points, and you can see if you had a string, you could take it around the outside, and no matter what point you were at around the outside of the ellipse, the sum of the two distances would always be the same. So those two blue lines would add up to some fixed number. Then if I connected it to somewhere else, now those two red lines would add up to that same fixed number because it's the same length of string. These two green lines would add up to the same fixed number. It's a constant if you add the two distances together. I can show you what that would look like here in a quick video. I know that the coloring looks kind of strange in what you're seeing. All right, so that's the idea that we were trying to get at before, that if you had two fixed points, two thumbtacks in the picture here, or two toothpicks in the other picture there, and you stretched a string out and went all the way around, you would get a perfect ellipse because the sum of the distances from those two fixed points would be constant. Now, an ellipse can either be a horizontal ellipse like this one, or it can be a vertical ellipse, and I want to draw a big vertical ellipse in your notes so that we can label some of the important parts of the ellipse. It's pretty good. Just like a circle, an ellipse has a center. But then instead of one radius that's constant no matter where you go, there are sort of like two radii, one for the short way and one for the long way. So from that center point, there are these 4 points that are sort of the furthest most points that you can get from the center, the furthest to the top, furthest to the bottom, furthest left, furthest right. And those 4 points are all called vertices. Each one is a vertex, and together they make 4 vertices. Now those vertices are not where the thumbtacks were. If you look back up in the picture up at the top, the thumbtacks are sort of inside the ellipse, and they're always going to be on the long radius. It's not really a radius, we're just using that word for right now. It's always going to be on the long direction of the ellipse. And those 2 points, each one is called a focus, and together they make 2 foci. Those are the important parts of an ellipse. An ellipse has a center, 4 vertices, 2 foci. And anytime we talk about an ellipse, you'll need to be able to find those important features. Now we said that these little lengths here aren't really a radius anymore because they're different in the two different directions. And what we have on this shape, and it's going to be kind of hard, your picture is going to get a little bit messy here, but you have a major axis, which is the long line going all the way from the top all the way to the bottom. So that distance is called the major axis. And the shorter distance, you could probably guess, is the minor axis. A little bit more vocab about the ellipse, words that pretty much make sense. The semi-major or the semi-minor axis would only be halfway across. So really that's more like a radius. A radius would be halfway. A diameter is kind of like the whole way, so the major axis is like a diameter. The semi-major axis is more like a radius. And we give that a special length, so it's not r for radius. The semi-major axis is length a units long. The semi-minor axis is again halfway across the minor axis. And that one is called b units long. We can try to label those distances in the picture. So from the center, the long way all the way to the vertex, that's A. From the center, the short way to one of the vertices is B. You'll notice I'm not saying up or down or left or right because it depends on which way the ellipse is facing. If it's a vertical ellipse like this one, A is up or down. The long way is up or down. If it's a horizontal ellipse, A would be left and right because the long way is left and right. We also need to define what are we going to call the distance from the center to a focus. And this one I remember because center has a C in it and focus has a C in it. That distance is called C. In your picture, it's this distance here from the center to the focus. That's C. We have everything defined. We have the center. We have 4 vertices, 2 foci, and then we have the A, B, and C marked out on our ellipse. Now we're ready to start writing an equation. First equation is A, B, and C are related by the equation A squared minus B squared equals C squared. That's a very important one. That is true for every ellipse. Good one to write down. That's not the equation of the ellipse, though. For the equation of the ellipse, I'm first going to remind you what a circle's equation looked like. A circle's equation was x minus h squared plus y minus k squared equals r squared. That's from 10.2. That equation is basically what we're going to use for an ellipse, except for there isn't just one radius. So we're going to have to incorporate the A and the B, the radius in the one direction and the radius in the other direction. Now if I'm writing an equation for this ellipse, the A was in the up and down direction, so the A is going to go underneath the y's. So I'm going to have y minus k squared over a squared. Again, if I'm writing one for this specific ellipse, the B was in the x direction, so the b squared is going to go underneath the x's. And this equals 1. That is our equation for an ellipse. That's what we call the standard form of the equation for ellipse. And in this case, this is the standard form for a vertical ellipse because the bigger number is with the y's. The only thing that would change if it was a horizontal ellipse is the A and the B would switch. So let's try some examples of what this would look like if we had a problem where we were trying to write equations for the ellipse. There's another picture just real quick of what the labeling would look like if it was a horizontal ellipse. In that case, the major axis runs left and right. The longer direction is left and right. The shorter one, the minor axis, is running up and down. But the vertices and the foci are all still in the same spot. Consider the ellipse graphed below. Write the equation of the ellipse in standard form and find coordinates of the foci. Standard form was that equation that we were just talking about on the last page, and there were two equations to use, one for a horizontal ellipse and one for a vertical ellipse. In this case, it looks like the long direction is the x direction, so we're going to be using the equation for the horizontal ellipse. The x minus h squared over a squared plus y minus k squared over b squared equals 1. The a is with the x's because it's horizontal. The h and the k, I guess I didn't say this explicitly, but the h and the k are from the center. So the center looks like 2, negative 4. So we're going to have x minus 2 squared and y minus a negative or plus 4 squared. For an ellipse, it's always a plus in the center here. So we can put a plus in. And for an ellipse, it always equals 1. Now the numbers underneath, the a and the b, were like the two radii. The a is going to be the longer one, the semi-major axis. And I'm just going to go to the picture and count it out. 1, 2, 3, 4, 5, 6. So a is 6. So we're going to put 6 squared underneath that. And in our final answer, we will go ahead and call that 36. Before we do that, let's figure out the b value in the b direction. Start from the center and count up to the vertex there at the top. 1, 2, 3 units to get to the top. So the semi-minor axis is 3. And we'll put 3 squared underneath the y's. For the final answer, all we need to do is write 36 and 9 on the bottom instead of 6 squared and 3 squared. That's part A. Write the equation of the ellipse in standard form. For part B, find the coordinates of the foci. Foci, to figure out where they are, we need to know what does C equal. Nowhere in the equation that we wrote is a C. But we have that other little equation, that a squared minus b squared equals c squared. That's the equation we'll use to figure out what C is, and then we'll be able to find the foci. Remember, the 36 is already a squared, and the 9 is already b squared, so just do 36 minus 9 equals c squared. It's not a very nice number. 36 minus 9 is 17. So c, not a very nice number, is the square root of 17. looking back at our notes, what does that mean? Well, that means that the distance from the center to a focus is the square root of 17. If the square root of 17 could be simplified at all, we would simplify it. That one doesn't break down and have any pairs, so we're just going to leave it as the square root of 17. Please leave the answers exact on the homework and on the test. Don't change them and make them decimals. Leave them exact. All right, so where are the foci? The distance from the center to a focus is the square root of 17. So if I look back at the picture, the center is there at 2 comma negative 4. And I need to decide to get to the foci, am I going to go up or down, or am I going to go left or right? Since this ellipse is longer in the left and right direction, the foci are going to be left and right from that center. So I'm going to start at the center, 2 comma negative 4, and go left square root of 17, which is about 4. And that's one focus. And then I'll count right square root of 17. And there's the other focus. So as I was counting to those foci, I started at 2, negative 4, and moved left and right. If I'm moving left and right, does that mean the x number is going to change or the y number is going to change? If we're moving left and right, it's the x number that's going to change. So we need to take that 2 and add the square root of 17, comma negative 4. It's still 4 units down to get to one focus. And take the 2 and subtract the square root of 17. Still comma negative 4 to get to the other focus. So those two together are the location of the two foci. For a shortcut, it is okay to write them as one ordered pair with a plus or minus. Now if it was a nice number, not the square root of 17, we would actually go ahead and add and get the coordinates and go ahead and subtract the square root of whatever to get the coordinates. But if it's not a nice number, usually we're just going to write our answer like this. Let's do another example. This time, instead of starting with a graph, we're starting with an equation. On that equation, they give us quite a bit of information. Now this one is pretty tricky. Just because the y's come first and the x's come second. So when you get the coordinates of the center, you just need to be really, really careful. The center is not at 3 comma negative 4. That has it switched up. The negative 4 is actually with the x, and the 3 is with the y. You'll see that often in the homework, so just be aware of it and be really careful as you're finding the center. Make sure the x number is coming first and the y number is coming second. They also want us to find the vertices and the foci. And to get those values, I really like to look at a graph. So let's sketch out a quick graph here of what this ellipse looks like. The center is at negative 4 comma 3. And then we need to find those other things. We'll take our cue from the equation. In the y direction, how many units do we need to move to get to the vertices? It's not 25, it's 5. 25 is like a squared. So we need to count 5 units in the y direction. So that means go 5 units down. There's one vertex. And go 5 units up. There's the other one. So what are the coordinates of those points? Well, this bottom one is at negative 4 comma negative 2. And the top one is at negative 4, comma, 8. People who notice patterns might have noticed that we just took the y coordinate there and added 5 and subtracted 5 to it to get those two values. Those aren't the only vertices though. We also have vertices in the x direction. So we'll go back to the equation and figure out how far we're going to move in the x direction. In the x direction, we need to move 3. So start from that center point and move 3 units to the right and 3 units to the left. Those are the other two vertices. So what are the coordinates for the vertices? Well, this one looks like it's at negative 1, comma, 3. And the other one over here is at negative 7, comma, 3. Those four together are the four vertices. To get the foci, we're going to do very much like what we did on the last one. To figure out where the foci is, we need to figure out what's C. To figure out C, we'll use the equation a squared minus b squared equals c squared. And in this case, 25 minus 9 is a lot nicer of a number. This time we're going exactly 4 units to get to the foci. What we have to decide though is, are the foci going to be left and right of the center, or are the foci going to be up and down from the center? The foci are always in the longer direction, so in this case it's going to be up and down from that center. We're going to count 4 units up, 1, 2, 3, 4 units up, and 1, 2, 3, 4 units down to get to the two foci. Since it is a nice number, we're going to write them as 2 ordered pairs. They're at negative 4, comma, 1, 2, 3, 4, 5, 6, 7, and negative 4, comma, negative 1. That is ellipses in general. Just like yesterday, you could FOIL out that standard equation to get to the general form, and you could complete the square twice to get to the standard form. In the second video, we'll do some examples of that. I'm hoping that you get into the second video still on Thursday. I'm just out of time to record it right now, so that's why there's a little bit of a break here. Start up the second equation and we'll do some examples where you're completing the square and working on getting it into standard form.